Good morning, everyone, and welcome to this session on prioritizing technical debt as if time and money matters. As you can probably hear, I have a horrible cold today, so my voice is a little bit off, and I hope it works anyway. And I won't let it hold me back because this is an exciting topic. So let's dive right in and see why prioritizing technical debt is such a challenge. It's a challenge that I like to think is well captured in something known as Lehman's laws of software evolution. And today I want to present the two main laws for you here and see if they resonate with your experience. So the first law of software evolution is the law of continuing change. Well, Lehman claims that when we build a system, it has to be continuously adapted and evolve, or it will become progressively less useful over time. Is this something you recognize? Yeah, I think so, right? Because this is the very reason why we are never done. Where we have to keep evolving our code, where we have to keep evolving our system. We have to add new features, right, required by users. We might even have to respond to competitors. But what I would want you to do now is to notice that there is some kind of tension, some kind of conflict to the second law of software evolution. And that's the law of increasing complexity. So when a system evolves, its complexity will increase unless we actively try to reduce it. And you see the tension here. On one hand, we have to continuously adapt and evolve our system, but when we do that, its complexity increases, making it harder and harder to respond to change. And the main challenge with that is that we can very easily end up in a vicious loop. And when we do so, we might not even notice it, because what we tend to see are symptoms rather than the root cause. And to make it worse, we tend to see different symptoms depending on who we are, what our role is. So as product people, what we tend to experience is that we get longer and longer lead times for implementing new features. That is, we get a longer time to market. And as a consequence of that, we tend to lose predictability, because if something used to take a week a year ago and now suddenly we need 2 months, then it gets even harder to guess when something will be done. And this in turn can put quite some stress on the whole team. And what also tends to happen in areas with significant complexity and high degree of technical debt is that you tend to evolve key personnel dependencies. We've probably all seen that, right? You know, those parts of the code that only a specific person can fix, and that person is on vacation. And our end users, what they tend to experience with increasing complexity is this. They tend to see bugs, which is an impact on the external quality of our code. And the real root causes tend to remain largely hidden, opaque, and obscured. So if increasing complexity and technical debt is such a vital component of successful software, right, to manage it, then what can we do to bring visibility to it? How can we visualize and bring visibility to technical debt? There have been several attempts over the year. One of them that is fairly common is to try to quantify technical debt. And the way it works is typically that you run some static analysis tool on your code that kind of checks what kind of violations do I have here against a set of predefined rules, and you sum them up and you get a number on the estimated technical debt you have in your code. The first time I saw this attempted was like 6-7 years ago. I worked with a client in the UK, and prior to my arrival, they had done something interesting. They had run one of these static tools capable of quantifying technical debt on their 15-year-old code base. And this tool happily reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. 4,000 years of technical debt. Just to put it into perspective for you, 4,000 years ago, that's here. That's the start of the recorded history through the invention of writing. So of course, I mean, one can speculate what kind of programming language did they use? Was it a Fortran? Was it a Lisp? What's around 4,000 years ago? I can't remember. But on a more serious note, 4,000 years of technical debt on a 15-year-old code base. Well, it could actually be possible because a lot of that technical debt, of course, grew in parallel by having hundreds of developers working on the code. But at the same time, how useful is it to know that you have 4,000 years of technical debt? Where do you start? How do you take action on it? Is all debt equally important? Most likely not. So what I wanted to show you with this story is that quantifying technical debt based on source code, it might be an interesting exercise. It's almost always depressing, but it's not particularly actionable. More importantly, technical debt just cannot be prioritized from code alone, right? The cost of technical debt is not, and I repeat, not the cost of fixing the code. The cost of technical debt is the additional time you have to spend with continuing changes to your code due to technical debt, right? So it's the interest part of technical debt that's fascinating, not the remediation cost. At the same time, we do have Lehman's law, right? So there's always this trade-off between improving existing code to make sure we can continue to maintain it and add new features versus doing what the business tends to push for, which is squeeze in more features. So we do need to prioritize. The question is just how. A set of techniques that I have been using over the past decade to address this is something I call behavioral code analysis. And behavioral code analysis is very different from a traditional code analysis because in a behavioral code analysis, it's always about code, people, and context. And context in this case can be your business decisions, it can be processes. And the core idea of behavioral code analysis is that the code, the source code, the way it looks now is important. It really is, right? Because we kind of need to distinguish good from bad. We need to identify overly complex parts. But that said, it's even more important to understand how we, as a development organization, interact with the system we're building. I'm going to try to make this much more specific for you. But before we go there, one of the prerequisites, and in fact, the only prerequisite for behavioral code analysis is that you have behavioral data on how we as software developers interact with the code. So where can we get that data? Well, the good news are you all already have it. We're just not used to think about it that way. Because what I'm talking about is this, our version control system. And you see a simple example from Git here. And those of you who have seen my previous talks or maybe read one of my books, you know that I'm a big fan of version control data. Yeah, I guess we all have our odd hobbies. Version control is mine. And the reason I'm so fascinated by version control is because for decades, we as an industry have been using version control, and we have used it mostly as an overly complicated backup system, and then occasionally as a collaboration tool. But in doing so, we have built up this wonderful data source on how our system evolved and how we, as people, have interacted with the code. So let's tap into version control and let's see how it helps us prioritize technical debt. And I want to show you how this works on a real-world code base. And for the first case study, I'm going to use a code base that some of you might have lying around on your desk, or maybe you carry it around in your pocket. I'm talking about this. I'm talking about Android. More specifically, I'm talking about the part of Android known as the platform framework base. And the platform framework base is a pretty large code base. 3 million lines of code, most of it written in Java by several thousand of developers, right? So it's software at scale. What you see here on screen is a behavioral code analysis visualization called Hotspots. So here I'm visualizing the whole Android source code. And I'm going to walk you through this visualization so that you know what you see. First of all, if you look at the screen, you see there are a number of high-level circles, the ones that blink on screen right now. Each one of those circles represents a top-level folder in the Android repository. So this is a completely hierarchical visualization that follows the structure of your code. And if this was your code base, you would recognize the names of those large circles as important subsystems or high-level components. It's also an interactive visualization so that I can click on it and I can zoom in to any level of detail that I'm interested in. And once I go to a lowest level of detail, I see that each file with source code is visualized as a circle. And you see that the circles, they have different size, right? And they have different colors. What does that mean? Well, let's have a look at that. And let's start with the size, because that's the easiest thing. Size is used to represent something called code complexity. That is, how hard is that code for a human to understand? And I'm going to talk much more about code complexity in just a minute and show you how I typically measure it. But before we go there, let me just point out, and I really, really want to make this clear. Let me point out that code complexity is the least interesting dimension when prioritizing technical debt. And the reason I say this is because code complexity has this property that it's really only a problem if and when we need to deal with it. So maybe we have these parts of a code that's been stable for 5 years. We never need to touch them. They just work wonderfully in production. They've been debugged into functionality. Even with a high degree of complexity there, I mean, it might not be ideal. It's not the situation we want, but is it really an urgent problem? Most likely not. We probably have other things that require our attention. So how can we figure out which complexity that actually impacts us? This is where behavioral code analysis taps into version control and looks at something called the change frequency of the code. We simply look at the number of commits that hit each file over time, and you sum them up and you use color to reflect that. And when you combine these two dimensions, then we're capable of identifying complicated code that we also have to work with often. And that's what I call a hotspot. We're going to return to this Android hotspot in a couple of minutes, but before we do that, I promised to talk a bit about this mythical thing called code complexity. Is there such a thing? And I have to admit, then when I talk about code complexity and technical debt, I try to avoid the term code quality because I never liked it. And the reason I don't like the term code quality is because it kind of suggests an absolute, right? Whereas reality is much, much more complicated. And that's something that's well captured in the following piece of research that I would like to share with you. So this is a fairly old paper, but it's still, I would say, 100% valid. And what's so interesting about this is that what this paper claims is that software complexity is a multifaceted concept, right? And we are simply doomed if we look for a single metric to kind of capture all of it. There is no such thing. So what can we do instead? What I have done is that I've taken a lot of inspiration from the second paragraph here that claims that if we want to kind of measure code complexity, right, then the most promising approach is to identify multiple specific attributes of complexity. We measure them separately, right? So we can capture the whole multifaceted space here. And I've been trying to formulate that into a concept I call code health. How healthy is our code? And the way it works is that we simply look at the research, because there is a ton of research on software maintainability and program comprehension. And we identify, based on research, properties of the code that are known to correlate with increased maintenance costs and an increased risk for defects. Then we measure each one of them separately, and then we can always kind of take those separate numbers, we can aggregate them, and we can normalize them so that we can present it. I'm going to show you what this looks like very soon. Before I do that, let me just show you a few examples on what kind of code health issues I typically look for in a hotspot. So I look at code health issues at multiple levels. One of them is like the whole class level, right? The module level, where I look for things like low cohesion. So low cohesion, what does that mean? Well, it simply means that the module has multiple responsibility. So maybe you're implementing 3 separate features inside the same module. And this is a problem because low cohesion makes the code much, much harder to understand. If I want to understand a module with low cohesion, I have to understand multiple different concepts from the problem domain, right? And I have to keep them in my head. And low cohesion also puts the code at risk for unexpected feature interactions, which are some of the most severe bugs we can ever have. Then, of course, at the function level, I look at things like brain methods. So brain methods are interesting. We've all seen them, right? So this is when you have this function. First of all, it tends to be a large function. It's overly complicated, lots of logic in it, right? And it's very central to the module in the sense that each time you add something to the module, you end up modifying the brain method. And over time, it just grows more complicated. Of course, I also look at different code complexity patterns. And to give you some ideas on what I look for something called deeply nested logic. So deeply nested logic is when you have if statements inside other if statements, and then maybe a while loop for good measure. The problem with deeply nested logic is that there is some very good large-scale research that suggests that roughly 20% of all programming mistakes are due to things like deeply nested logic. It's also pretty easy to avoid once we identify it. Anyway, with that said, once we have the numbers for all these different issues, then we can of course aggregate them, and we can visualize a map just like we did for hotspots, but for code health and code complexity. Here's an example. So this is a different code base. This is Kubernetes, and it's the same visualization style, but now each color tells us how complicated the code is. So everything that's green, that's perfectly healthy code I can expect as a developer to pick up. I will be able to understand it and modify it safely. And then we have the yellow area, like the warning space, right? So we have a number of issues here. They tend to be quite severe, but they're not as severe as the red ones, which indicates that we basically tick all of these boxes, right? And the interesting thing is that once we have a complexity dimension, that in itself might be interesting, but it's most useful when combined with the hotspot visualization. Because what we can now do is that we can look for this overlap between code complexity and change frequency, that is relevance. So we see here in this example in Kubernetes, there are plenty of modules that seems to have overly complicated code, but, and here are the good news, only a few of them are hotspots. So hotspots actually sends a good message, right? It's a positive message, because hotspots tell you that no, you don't have to fix all your technical debt. And the reason I say this is shown in this graph. And please look carefully, because this might be the most important graph that I'm going to show you today. Because what this graph shows you is that on the x-axis, you have each file in a specific system. And those files are sorted according to this change frequency. That is, how often do we modify that part of the code? And the number of modifications, it's what we see on the y-axis. Now, if you look at this graph, you see that it forms a very clear power law shape. And this is nothing unique to Kubernetes or Android, right? Over the past decade, I've probably analyzed 300 code bases, right? And this is a pattern that I found in every single one of them. So this seems to be the way software evolves. And this is important to us, because what it means is that in your system, most of the code is going to be in the long tail. So that's code that's rarely, if ever, touched. And that's the part of the code where we, as an organization, can typically live with a certain degree of technical debt. And that technical debt has low interest and low risk. On the other hand, we see that in this graph that most of the development activity is in a fairly small part of the code base, typically 2 to 4 or 5% maximum. And that's what the head of the curve identifies, right? So that's what you find with hotspots, which are those files at the head of the curve. And what we can now do is that we can zoom in on them and make sure that we have identified any code health issues, any complexity issues, because any excess technical debt in a hotspot is likely to become very, very expensive due to the high change frequency. All right, that was hotspots. Let's move on and see how actionable this is. And let's do that by returning to our Android case study. The number one hotspot in Android when I did this analysis was a module called Activity Manager Service. Isn't that a wonderful name, by the way? First, you have activity, which could maybe be something from the problem domain. But then you have two words, manager and service, and each one in isolation kind of suggests a module with low cohesion. Now combine them, and combine that with the fact that you have 20,000 lines of code in this module, right? So even if we know that this one is overly complicated, right, then a high degree of technical debt and all of that, I mean, where do we start? Do we refactor 20,000 lines of code? I hope not, right? I hope that you're all shaking your heads, because no, we should never, ever take on refactorings at this scale, because they're going to be extremely risky. In particular, when we consider that just over the past 3 months, 74 developers have contributed code to this module, right? So it's going to be high risk to try to refactor that. So what do we do instead? Well, what I do is that I use a technique called Hotspot X-ray. So here's how it works. When I find a large hotspot, what I do is I take it and I parse it into separate function blocks. And then I look at the Git log and see where do each commit hit over time. And I sum them up and I get hotspots at a method level. Let's have a look at the X-ray of Activity Manager service. As we see, the #1 hotspot in the Android hotspot is a method called handle message. And we see in the first column, change frequency, that this method has been modified 98 times just over the past year. So like 2 times a week, some developer is impacted by the excess complexity of this method. And we can get a very quick indication of how complicated this method is by looking at the last column that says cyclomatic complexity. Now, some of you are probably familiar with cyclomatic complexity. It's a pretty old complexity metric, where what you do is basically you count the number of possible execution paths through the function, right? And you sum them up. And cyclomatic complexity isn't really a particular good complexity metric. The reason I use it is because cyclomatic complexity is pretty good at one thing. It's good at telling me how many unit tests do I need to cover just this function. And for handle message, the table here says 101. So I would need 101 unit tests to just cover this function. That for sure tells me something about how much logic there is and how complicated this function is. If I now look at the column in the middle, I see that the number of lines of code is 500. 500 lines of code, that's a lot for a single function, isn't it? It is. But let me tell you this, 500 lines of code is much less than 20,000 lines of code, which was size of a total hotspot. And 500 lines of code is definitely less than 3 million lines of code, which was size of a total code base. So more important, I'm now at the level where I can act upon this information and do a focused refactoring based on how we, as an organization, have interacted with our code. All right, there's one more thing I would like to share with you. Because when talking about technical debt, we should talk about the people side of it as well. And the reason I say this is because getting the people side of software wrong has killed more projects than even Visual Basic, I promise. So we're going to talk about this subject by talking about legacy code. Because legacy code is frequently confused with technical debt, but the two are slightly different. So what is legacy code? Well, the definition I use is that legacy code is typically used to describe code that, first of all, it lacks in quality, and second, and even more important, that code isn't written by us, right? So if we tick these 2 boxes, then it's legacy code. And this has important implications for us. So let me share you a story with you, what happened to me a couple of years ago. So what happened was that I did a workshop for a company, fairly large company, and I had one team in the workshop. And what we did was we did a hotspot analysis of their code base. And they actually had 2 products that they were maintaining. So we did a hotspot analysis and we looked for potential code health issues. We tried to prioritize the tech debt, and we did find some, and it was fairly straightforward to kind of categorize it and make up a plan for it. But overall, both code bases looked pretty good. However, then someone told me that, you know what, we actually have a 3rd code base as well. So I said, okay, interesting. Let's have a look at that one. And the whole team kind of glanced at each other and said that, yeah, but we don't really have to do it because we know the 3rd code base is a mess. So I said, perfect, that's even more interesting. Now we do have to look at it. So we did. And it turned out that the 3rd code base came out just as good as the other 2. And the team were a little bit skeptical at first. So we kind of had to spend some time looking at the code and actually inspecting it. And it turned out that there was objectively no difference in code complexity between the two first products and the third one. So how come that the third code base was considered to be so much more complicated? Well, it turned out that code base number 3 was originally written by a completely different team in a different part of the organization. That team had since been disbanded, and the new team had simply inherited the existing code. So the reason that they felt that code base number 3 was hard to understand and messy had nothing at all to do with code quality or code complexity, right? What it had to do with was a lack of onboarding, an unfamiliarity with both the solution space and the problem domain. And trying to address that problem by starting to refactor and pay down technical debt would simply be a waste, right? Because you're solving the wrong thing. Now, this story kind of made me think a lot back then. So I started to think, if it's this easy to create legacy code, how quickly could you take your own code base and turn it into legacy code? What would we need to do? So I would like to show you how this works. And I'm going to look at another real-world code base. This is a code base from Microsoft called ASP.NET MVC Core. And it's a code base that some of you might be working with. It's a C# framework for building dynamic web applications. And you see the hotspot visualization here. ASP.NET MVC Core is significantly smaller than Android, right? So it has roughly 180 contributors, maybe 350,000, 400,000 lines of code, and mostly C#. Now, if you remember the hotspots, right? And I showed you this power law curve. What's so fascinating about software evolution is that power laws are everywhere. So if we look at the contributions of these 180 people that have contributed to ASP.NET Core, and we plot them in a similar graph based on how many lines of code have they written in that particular code base, then we quickly see that we get a power law as well. And I know that ASP.NET MVC Core is an open source project. It's a popular open source project. The thing is that I have seen exactly the same power law on most commercial closed source projects that I've analyzed as well. So again, this seems to be the way that code evolves from the people side. And what this means is that in most projects, you simply have some core contributors. They might have been around for a long, long time, right? They might have followed along with the system. And they have typically written a significant amount of code. So if we talk about this from a legacy code perspective, what's the impact if one of those people leave? What's going to happen? Well, what's going to happen is obviously that we're going to lose some detailed knowledge of how that code works. And for sure, we can mitigate that via pair programming and stuff like that, right? But still, at some point, if people leave, then we're going to lose knowledge. So what can we do? Well, we can investigate it using behavioral code analysis and see what is the impact. We can actually simulate it. So how do we do that? Well, let's return to Git and let's look at the version control data. The beauty of version control data is that version control knows exactly which person that wrote which piece of code. So this is something that we can kind of summarize. We can even aggregate it into teams, and we can use it to talk about things like legacy code risks. So let me show you how this looks on ASP.NET MVC Core. What you see here is the same visualization style as I used for the hotspots, but again, the color carries a different meaning. Everything that you see here that's blue, that's code written by the current team. So this is code where someone in our organization has an active working knowledge of this code, right? And that's always a good thing. The different shades that you see of gray here, the different shades of gray, they represent existing knowledge loss. That is code written by former contributors, right? So this is a case where someone has already left and we have like a black hole in our system mastery. Now, what we can do using version control is that we can simulate the impact if one of these core developers leave. So I did this on ASP.NET MVC Core. I simply went and looked at the contributions and picked one of the persons who have been with that project from the very start and said, what's happening if given these 180 offers? If just that one person leaves, what's the impact? And you're going to see it to the right, indicated in red. Wow. If this was your project, should you be worried if this was a real world scenario? I would be really, really worried, because we lose a lot of knowledge here in multiple different areas. So what would I do with this data? How would I use it? Well, what I recommend is that if you have a lot of potential knowledge loss like this, it kind of clearly indicates a lack of knowledge distribution. And if this is a real world scenario, what I would do is that I would take this data and combine it with the hotspot data to mitigate offboarding risks. And the process I use for this is that I simply look at knowledge loss or abandoned code via two other properties. So first of all, if I see that a developer is leaving, we're going to lose knowledge of a piece of code, then I know that's an issue. I can then use the hotspots to say, how relevant is this? What's the likely impact? Because if it's a hotspot, then it's very likely that will continue to work in that feature area. And if it also has a high code complexity, then I know it's an issue for sure. So if I tick all these three boxes, then I know that I have a very real offboarding risk. And what I typically do to mitigate that problem is that if I have the possibility, I pair together the original developer with the person who's going to stay. And I have them refactor those hotspots together to mitigate the upcoming risk. The reason I showed all of this to you is because I wanted to clarify that there is so much more to code complexity than just the code. And when we talk about prioritizing technical debt, this is really, really important to keep in mind. In particular, that social factors like familiarity and system mastery influence how we perceive the code. And it's very easy to overestimate the complexity of unfamiliar code. And using behavioral code analysis can kind of help you get objective numbers on that can guide your decisions. And that brings me to a last thing I want to share with you today, that these techniques, they don't really replace anything. Rather, what they do, behavioral code analysis is here to complement your experience and your expertise, because software development at scale, it's a really, really challenging problem. And I'm convinced that we as developers, we need all the support we can get. And I hope that this session has inspired you to investigate the field in much, much more depth. And if you want to dig deeper, I have my new book out called Software Design X-rays that covers Hotspots, X-rays, and several other behavioral code analysis techniques, including scaling these to microservice systems. So if you're interested in diving deeper, I highly recommend that you take a look at it. If you want to see behavioral code analysis in action, then you can check out codesyn.com, where I have prepared a number of interactive showcases that you can access and explore existing and well-known open source systems and see if you can find any hotspots in the code that you might be using. And of course, if you want to try this on your own code base, it's also possible at codesyn.com. I blog regularly about these techniques at codesyn.com, my blog there, and occasionally at adamtornhill.com. Now, before I leave time for questions, I'd like to say a big thanks for everyone for showing up this morning. Thanks a lot for listening to me, and may the code be with you. Thank you.
Wow, that was such a nice talk. Thank you so much, Adam. It was very insightful, at least for me. We do have some questions here on Slack. Of course, you can engage with them later on as well. But mainly, the question is, what's the tool that you're using for? Is there a tool you are using for analyzing the code base for tech debt? And then kind of similar question is, what tool was used to analyze the Android code base? I guess you already addressed that afterwards in the talk, but if you want to give a few words for the tooling, maybe.
Yeah, sure. I'd be happy to do that. I used CodeSyn to analyze Android. And in fact, I used there's a free community edition of CodeSyn that you can use. So I also had, when I started out working on these techniques like 10 years ago, what I did was that I started out writing a bunch of scripts to kind of try to get the data, right? And I packaged those early programs that I did into an open source project called CodeMat. And I quickly kind of ran into a number of limitations. First of all, that Git data is quite noisy. So there are tons of stuff that we do to our Git data, like we rename a folder, or we move a file, or we extract a segment. And kind of parsing and tracking all of that is quite challenging. So I've been spending the past 6 years on building CodeSyn to make sure we can automate all of this so that we can get a flawless experiments, so kind of focusing immediately on tech debt. So if you enjoy these techniques, then please consider to support CodeSyn.
Awesome. Yeah, sounds great. Do you analyze code depth in CI? I guess continuous integration.
Yes, we do that. So we, and it's a very interesting question actually, because I wrote about that in Software Design X-rays, that if you look at the research, when is technical debt introduced? For many years, I kind of thought that the way it typically works is that you have some code. The first iteration is always flawless, right? It looks good. And then we have some pressure that makes the code get worse. But looking at the research, that's not what tends to happen at all. What tends to happen is that when you have technical debt and you trace it backwards, then that technical debt was most likely introduced in the very first version of the program. And from there, it just went downhill. So that means that the earlier we can catch any technical debt, the more, the more important it is, right? The earlier we can act, the better. So what we did in CodeSyn was that we built in pull request integrations, and we built an integration for CI/CD so that you can kind of get alerts and even stop the build when things like that happen.
And is it possible to integrate it with different tooling, like let's say GitHub, DevOps, Azure, whatever it is called, and that kind of things? I think it's possible to integrate it there too.
Yeah, it is. It's, I mean, there are multiple options. If you run the SaaS version at CodeSyn, then you just press a button and you integrate with any of those 4 big providers.
Awesome, nice. Thank you. That's very useful. I think could be something that we want to try really. There is a little bit longer question. Isn't tech debt created by the developers due to lack of architecture knowledge, guidance, and personal motivation to have it clean, which not always which is not always about complexity, but speed as well. I need it now, so we'll do shortcuts. Why business should pay for it? That's the question.
Yes, and I think that's like the core problem with technical debt. So first of all, the reason there is behavioral code analysis was because 10 years ago in my previous life, I used to be a software consultant. And I very often consult in some kind of technical leadership role, so a tech lead or a software architect or something like that. And one of my challenges was always to kind of be that communication bridge between the engineering organization that kind of, were impacted directly by technical debt. They knew where it was, right? They knew that this part is a mess. And the business organization product that kind of pressed for new features. And going to a non-technical stakeholder and start to talk about things like code complexity or cyclomatic complexity or dependencies or whatever, we're just going to lose them. They speak a completely different language. It's not that they don't care, but they don't understand what we're telling them. So that's why I think that techniques like behavioral code analysis can really, really help and facilitate that coordination and communication. So I had myself for years used things like a hotspot map. And in my experience, non-technical stakeholders, and I've been presenting to CEOs, right, top-level management, give them a 2-minute explanation and they understand it and they like it because it tells them that, yeah, we have this massive code base, but we can focus on just this part. So that's communication is like, I would say, like the foundation. Then to kind of tie back to a question, yes, there are tons of other aspects that are important as well. So the architecture, how you align your teams with the architecture, right? The whole Conway's Law thing. And I have a couple of blogs on that. If you look at codesyn.com, I blog there. And I also have, I think, 2 chapters on that in Software Design X-rays, because you can get a lot of insights into your architectural side and the team side with behavioral code analysis. And I think it's a space that's at least, if not even more important than the code complexity space.
Thank you. How to avoid these pitfalls when starting out on a new project to avoid them in the first place?
Yes, great question. So the answer is visibility, visibility, and visibility. And the reason I say this is because I've seen several projects, right? Very typically it's legacy migration projects, or rewrites. We say that, yeah, we have this messy code base. It's earning us money, but we cannot maintain it anymore. Let's do a new code base. And you start out with the best of intention. This one, everything, this time everything's going to be perfect. What very soon happens is that there's an external event. And that external event is almost always a deadline, right? Someone pushes for some kind of delivery. And I have been seeing systems like that, right, where the technical debt is kept very, very low and then it just spikes. And once you have taken on technical debt, it's extremely expensive to reverse it, right? So you kind of stay at that high level. So having techniques like behavioral code analysis, where you can visualize the evolution of your code on a daily basis, is the best protection, the best insurance you can have against that.